A very good morning, good afternoon, good evening, my dear friends. Welcome to this TQM 1 lecture series under NPTEL MOOC, and I am Raghunandan Sengupta from the IME department, IIT Kanpur. So, we have finished 30 lectures, which is 6 weeks. So, we will continue another 10 of them to complete the whole set of 8 weeks lectures. So, this is the 31st one. Now, if you remember in the end of the 30th lecture, we were discussing that depending on as the sample size change, which means you have to find out the central line, the upper control, lower control, and obviously it would mean that the values of the standard deviations would change, because if you remember there is a factor of n which comes in the denominator generally for the case of binomial distribution. So, the standard error of the sample or the standard deviation of the sample. Standard error is a technical word which is used, and that value is given by square root of p into 1 minus p by n. So, this n becomes n1, n2, n3, n4 depending on the number of sample size which you have for each set of observations, and these p they need not be the actual value from the population, they would be basically estimates taken from the sample. And based on that, another concept which also came up was basically to find out the average sample size, like rather than changing it for the first set of observations from n1, then it changes to n2 for the second set of observations. You find out the average, which is basically n bar, and use that for our calculation. So, in the first case, when you are changing the sample size, the upper control and the lower control lines keep changing. So, if you remember in the last class, we were drawing short horizontal lines which basically denoted the changing UCL and the LCL, but for the average sample size being constant, which you find out, which is n bar, you will have a constant upper control and a constant lower control. Based on that, you do the calculations. So, we were just trying to complete one problem. We found out the n bar, and we drew gave the information set based on which you can find out the calculations to find out the central line, upper control, lower control, and then we draw the graph. So, this is what I am going to show now, the graph. For the control charts, when you want to find the errors, now also I am again mentioning it the second time. Generally, the non-conformity problems were also an idea based on which you can draw the or basically have a look at the control chart. So, this was basically a non-conformity which we are basically studying. So, if you measure the non-conformity along the y axis and along the x axis, as you see, you have the sample number. So, if there are averages, which is the average value of the sample size, you see the changing errors which are given in the line diagram. So, this is the line diagram which you have, where I am just hovering my pen, I am not drawing over it. So, it goes like this. So, they are always between the upper control limit, which is 0.1894, and the lower control limit, which is 0, and the average number of errors comes out to be 0.074, which I am just circling. So, if you write the R code, so the R codes are giving just as a boost up concept, which anybody would be interested to take up. And if you learn R, it really helps in trying to solve different type of problems, either in statistical quality control, total quality management, or in the area of statistics and all these things. So, you have a matrix of size 20 cross 2, and you have the sequences of numbers given from 2, 3, 8 till the last 3 being 3, 7, 4, and then basically you find out the average values, draw the upper control, lower control, and basically name what is the nomenclature of the graph. So, this is the group summary statistics are given along the y axis, the groups of the sample number is given along the x axis. You have the upper control limit, the lower control limit. Upper control limit is basically 0.1894123. So, if you keep it to 3 decimal places, is more than enough to solve the problem. The lower control limit value is 0, and the central line is given as 0.074. Based on that, you find out if there are any aberrations in the set of observations or they are out of control. So, for this diagram we see they are not out of control. So, we basically will now study alternative probability models for count data. So, what are these? I will try to explain. So, most applications of the C charts, the conformity charts which we just considered, assume that the Poisson distribution is true. Now, again to step back, I am not changing that course of discussion, but remember that whatever the distribution be, maybe it is binomial, maybe is Poisson, maybe is exponential, if you keep taking observations, then in the long run if you draw the histograms will slowly mimic the normal distribution. Now, which means that the whatever the distribution underlying distribution was, the conglomeration of the samples which you are going to take, the sample characteristics would slowly basically mimic the normal distribution, and the corresponding mean and the standard deviation of the normal distribution would be something to do with what is the original distribution based on which you are trying to draw the standard normal distribution. So, this was basically the essence of the central limit theorem. So, continuing that, let me read the first bullet point again. Most applications of the C chart assume that the Poisson distribution is the correct probability model underlying the process. So, there would be other distribution for other cases. In the Poisson distribution, the mean and the variance are equal, which is true. So, this may not be actually true in all the cases, that is absolutely true. So, what we will try to do is that try to find out some other distributions which basically mimics the so called population characteristic based on which we are trying to do the study. So, mixtures of various types of non-conformities can lead to situations in which the total number of non-conformities is not adequately modeled by the Poisson distribution. So, obviously, it would mean that the Poisson distribution based on which we are trying to draw find out the limits and then try to find out that how the overall process graph changes may have an error because the Poisson distribution by itself is not true. Also, when the count data has either too many or too few zeros may be a problem, because in the Poisson distribution is a discrete one, and in the discrete case we want to find out what are the numbers. So, if there are numbers, so obviously they would basically denote, consider like this, the number of defects or the number of good items we want to find out. So, if there are too many zeros or fewer zeros, then obviously the Poisson distribution may not be the actual case which will give you that information. Now, remember that one of the basic theories in probability was that in case if you have a distribution where consider for the binomial case, if the sample size n. So, this n and the sample size which we take for the drawing this charts are different, technically different. So, if the sample size and the parameter p, which is the proportions of good items or the proportions of bad items, whichever you look at and whichever you analyze the problem, if n is very large and p is very small, then obviously it can be mimicked by the standard normal deviate. So, there is a theoretical proof for that, but I am just stating it where things would be much clearer, that depending on some assumptions, whatever the underlying distribution is, whether discrete or continuous, it can be mimicked by the standard normal distribution or the distribution which is normal with a certain mean and a certain variance. So, what are the assumptions? That will become very relevant depending on the problem. So, to continue, so geometric distributions can also be used and as a model for count or event data. So, how many number of times that thing is occurring. So, it can be, say for example, I want to find out that consider again going back to the same example, may not be the exact very best example for this discussion, but let us consider this. Say for example, you are checking number of very high advanced technology equipment. Again I am saying that you are using it for a fighter jet or using it for in a pacemaker or using at a very high ended thing, consider a bridge over which lots of traffic goes or a train pass. So, any error obviously would be disaster. So, what we want to check is that the moment we find out one error, obviously we will reject that. So, based on that we are trying to use the model which is the geometric distribution. So, we want to find out that if an error has a probability of p, so then obviously the probability of not having an error would be 1 minus p. So, the moment the first error occurs, you will basically take corrective actions and basically make a note of that. So, the probability model for the geometric distribution is given as p and 1 minus p, which is basically x minus a. So, basically x would basically depend on the number of observations you are taking, and a can be 1, 2, 3, x can be a plus 1, a plus 2, a plus 3, depending on how you have framed the problem. Suppose that the data for the process is available as a subgroup of size n, and the observations are x1, x2, x3 till xn. So, they would be independently and identically distributed. Based on that, you can find out what is the expected value, what is the variance, and then considering the central limit theorem is true, you basically use the standard normal deviate, but use the normal and the variance of the standard normal deviate or the normal distribution as those coming from the actual distribution based on which you are trying to draw the normal distribution, which in this case is basically the geometric distribution. But obviously, it would mean that technically if you take more and more observations later on, then the normal distribution would basically be the best distribution which would mimic the actual population distribution, but with changed mean and change variance, which I am again mentioning are the actual expected value and the variance for the population distribution from where you are trying to pick up the observations. So, they can be basically two statistics which you can use. They would basically be the total number of events. So, the total number of events would be counted at x1, x2, x3, x4 till xn, and generally we would be interested to find out what is the average number of total number of events. Events may be either, say for example, good items are passing, events can be either bad items are passing, events can be, say for example, white color boards being produced. So, depending on whatever your outlook is. So, you find out the average would be basically sum of x1 to xn divided by n, and then if you find out the means and the variances, they would be given as mu suffix t and sigma square suffix t as given here, which I will try to highlight. And you will use this mean and the least standard deviation as the mean and the standard deviation for the actual normal distribution based on which you will do the calculation. Now, if I want to find out the mean and standard deviation for the average number of events, they would basically be divided by n, and we get the mean value and the variance of the standard deviation. Standard deviation would be the square root of the variance as given here. So, Kaminsky refers to the control charts for the total number of events as the G chart, and the control chart for the average number of events is basically H chart. Based on that, you can basically have the G chart and the H chart, which will give you a lot of information that how the average value in the standard deviation can be made, or you can utilize that to draw the process control charts, which will give you a lot of information how the process is going, whether there is an assignable causes or non-assignable causes, and you can take corrective actions as needed. So, control limits for the G and the H charts as just discussed. So, you have the central line, which for the two cases would be like, in the total number of events charts for the G charts would be given by this, which I am writing using yellow highlighter, and then you will find out the corresponding standard deviation of the variance and use them as the control limits, like mu plus minus k sigma. Now, this k value which I am saying is again is basically the overall confidence level or the level of confidence we want to use. So, then you will see that you find out the value of the standard deviation, again the standard deviation. So, this plus and minus I will again use a different color to make our understanding much clearer. So, this plus minus and this plus would basically denote to what positive value onto the from your side, if you are looking onto the right hand side it will go, and what is the negative deviations of the dispersion you will have on the negative side. So, these if you remember, they would technically be the standard deviations would be square root of n into 1 minus p by p square. Now, if you come to the values of the central line and the upper control and the lower control depending on. So, let me again change the color So, this is the average number of events charts, which is H. Then let me again highlight the average value. So, the average value is basically, so as you divide by n, so obviously those changes would be there. So, it is 1 minus p by p plus a. So, you use that as a central line. And again let me highlight the values which I have for the standard deviations are these values, which is square root of 1 minus p divided by n by p square. Now, why it is coming n square is n is being divided, because n would basically for the variance would become a square. So, once it goes into the denominator, it would be calculated accordingly. And continuing our discussion, we find, and you also state, the plus value and the minus value are exactly as mentioned. So, they are plus L minus L, again it will depend on the level of confidence. So, this p hat would basically be given by the ratio of 1 by x double bar. X double bar is the actual average, average of the average minus a value. So, the a value which you already know and has been calculated, and it can be utilized accordingly. So, this calculations would be used for when the total number of events is given, which is 8 charts, and this would be used for the case when the average number of events are given, which is the H. That was the initially, sorry, that was the G chart, this is the H chart. So, the control limits are based on an estimate of P. Suppose that there are m subgroups. So, you have, as I mentioned and as we have discussed in the 30th lecture. So, we had subsamples. We take the first one, the second one, third one, fourth one, and continue taking, and we take m number of such set of observations. And in each, initially if the sample size was fixed, we took n observations in each set. Now, that is what we are discussing, and later on we saw that we could change the sample size also in each subgroup. So, continuing the discussion, suppose that there are m subgroups available, each of size n. So, the size n is not changing, and let the total number of events in each group be T1, T2, T3 till Tm. So, the average numbers of events per subgroup would be given by sum of T1 to Tm divided by m. Now, if you want to find out the total number of events chart, which is the G chart, and the average number of events chart, which is the H chart, the concept is exactly the same. Now, what you do is that, let me use a color which is easily discernible. So, this average basically comes as the central line in this case, and in this case it basically gets divided by n, because I am talking about the average number of events charts. So, obviously, in technically in that other example also it was basically divided by n. Now, the corresponding standard deviation for the G charts, where I will again highlight, is given by this, not the L. L part is the level of confidence. Here in the other case, the standard deviation is given by the circle part. Here only you should remember it is been divided by square root of n. Now, why square root of n? Because if you divide by n, you want to find out the variances average, but then you want to find out the standard deviation, it should be divided by the square root of n, that is why. So, it technically is divided by n, then later on in the next stage when you find out the standard deviation, it is divided by square root of n. So, again the same concepts comes, you plus minus, you add some plus minus values of L. So, those L would basically give you the level of confidence. So, here also, so the control limits based on the estimate of P are found out, and you have basically the G chart and the H chart, which will give you the information as just stated in the slide. Now, procedures for variable sample size. So, control charts for non-conformities are occasionally formed using 100% inspection of the products. In this method, the number of inspection unit in a sample would usually not be a constraint. So, if a control charts for non-conformities, which is basically the C charts, is used in this situation, both the central line and the control limits will vary with the sample size. So, as the sample size changes, so obviously the central line and the upper control and the lower control would change, because in this case the upper control and lower control would basically be dependent on the central line, based on which we will need to recalculate it. Such a control charts would be very difficult to interpret because they are changing, which means the central line is changing, the upper control, lower control values are changing. So, what we want to basically compare against the central line, that would also be very difficult for us to infer. The correct procedure is to use the control charts for non-conformities, which is per unit, which is the U charts. These charts will have a constant central line. However, the control limits will vary inversely with the square root of the sample size. So, generally the U charts will have a central line which is fixed, but the upper control and the lower control values would basically change depending on so called the sample size, because that will be divided by n in the case of variance, and once you take the standard deviation it would become basically divided by square root of n. So, you have to understand it technically and do the calculations as necessary. So, let us consider an example. Here in the textile finishing plant, dyed cloth is inspected for the occurrence of defect per 50 square meters. The data on 10 rolls of cloths are shown. So, basically it goes from roll, which are given by number 1 to 10. Number of square meters is given starting from 500 to 625. Total number of non-conformities in each roll is given. So, the first one in 14, second is 12, till the second last is 19 and 23. So, the number of inspections units in roll, whatever the roll number is basically n, is given as 10, 8, 13, and the last two values are 12 and 12.5. So, the number of non-conformities per inspection unit are found out. So, based on that you will try to basically recalculate and draw the chart, so that it will give you a much better perspective where the process and how the process is going. So, based on that we do the calculations and find out u bar as 1.42. In the other case, for calculation the control charts, so ni's are given. So, these are the sample size which are changing from observation, set of observations to observations. So, the first one was basically the ni's were given depending on the values of the calculations. So, once you find out the upper control limit, which is basically u hat plus 3 of into multiplied by the term which gave us the standard deviation, and minus value would again be minus 3 into that term which gives us the standard deviation. So, if you draw that, so the computer will, or the chart which we have in front of us, which is in figure 7.17, gives you the subgroup numbers which are noted along the x axis, and along the y axis you have basically u, and the central line would basically be u bar, and the fluctuations would be basically found out using the so called change values of the, or the recalculated values of the standard deviation. So, operating characteristic curves for both the C and the U charts can be obtained from the Poisson probability distribution. For the C chart, the OC curve plots the probability of type 2 errors against the true mean values. The expression of value of beta is given. That given C, whatever the value C is, that we want to find out the probability of x being less than the upper control or x being less than the LCL, and basically you find out the difference of this probability and can comment on what is the value of beta. So, let us consider an example. We generate OC curves from the C charts as given in sample example 7.3. For this example, since lower control limit is 6.48, upper control limit is 33.22, the equation would basically yield the value of beta, which is now difference of two terms. What are those terms? One is the probability that x is less than 33.22 given a certain value of C, and the other value which will basically subtract from this initial value is the probability that x is less than equal to 6.48 given again the value of C is known. So, since the number of non-conformities must be integers, this is equivalent to basically trying to find out. So, 33.22 becomes 33 and 6.48 basically becomes 6, and you do the calculations to find out. These probabilities are evaluated in and given in table 7.13. The OC curves is shown in figure 7.19. For the U charts, we generate the OC curves from the following. So, say for example, we have the beta value is given by x being less than equal to UCL given some value of u, and the x being less than equal to LCL given some value of u. So, based on that again you basically multiply the value of n on both on the left hand side and the right hand side, and you get the so called numbers, not proportions now, they would be on numbers. So, you basically put the numbers and you find out what is the control limit for the value of x, which is basically in between n into the lower control limit. Lower control limit is basically coming from the proportions. So, proportions multiplied by n would give you the numbers. So, obviously, they may not be in exact integers, you have to basically find out the numbers in decimals and then basically extrapolate them according to whatever your decision is. So, say for example, if it was 32.13, then obviously I will be tempted to take the 33 number of observations, so which is n. So, based on that you find out the sum of this value of the OC curve values. So, the OC curves would basically be the integration values of e to the power n into u. So, u value was also there, now the n value is coming because that is the total sample size you have taken. So, based on that you find out what is the value of beta. So, example, let us continue. Calculate the OC curves for C charts with upper control limit as 33.22 and the lower control limit as 6.48. Column 1 gives you the C value as 1, 3, 5, 7 till the second last one is 40, then 45. Then the probability that x is less than equal to 33 given some certain value of C, whatever it is, it basically ranges from 1 to 0.038 depending on where C is, and then you can find out the probability that x would be less than equal to 6. So, this is considering the lower control limit. So, these probabilities are given as 99.9% till about 0. So, difference between that in decimal system will basically give you the fourth column, which is the value of beta. So, the OC curve of a C chart with LCL as 6.48 and UCL as 33.22 is basically shown. You can basically solve it using the same concept as discussed. So, low defects, we are interested to find out that what is the reason and what are the causes for defects and how they can be made low. In general, technically we won't want any defect, but that is practically not possible. So, we will have defects and how you overcome that. So, we saw that using different type of charts and tables. When defect level in a process becomes very low, say for example, under 1000 occurrences per million, so there would be very long periods of time between the occurrences and the non-conforming unit. In these situations, many samples will have 0 defects and the control charts with the static consistently plotting at 0 will be relatively uninformative. So, it will not give you any information, and conventional C charts and U charts basically in those cases would become defective. So, create a time between the occurrences of control charts which charts a new variable, and the time between the successive occurrences of this events are noted out such that somebody can basically take some collective decisions based on that. So, with this I will end the 31st lecture and continue discussion the charts further on from 32nd and so on and so forth. Thank you. Have a nice day.